This meeting is being recorded.
In section 2.8, we're introducing what's referred to as curved arrow notation, or curved arrows in general. So what these curved arrows will accomplish is electron movement being shown. So we know from collision theory that two molecules have to collide in order to interact or to, react. And bonds are broken when that happens, and new bonds can be formed. And what we should know is that there's electron movement that occurs when these bonds are broken and bonds are formed. So we need to show this by using, in this case, we're going to use it showing an arrow. The tail end of the arrow here, we're going to learn is where electrons start, and then the head shows us, right, the other side here with the point shows us where the electrons will end up, where they will go. So the arrow starts, the tail where the electrons are located, and then the arrow ends, the head where they will end up after the electron movement. So here we see a double bond, and these electrons are moving over here. So what will this look like when these electrons move over here? Will that formal charge still be there? We'll take a look in a second. But this last point here notes that we're going to explore this again in chapter 3 when we look at acid-base reactions. So if you recall, acids and bases can be defined multiple ways as Arrhenius acids with H plus and OH negative. Then we can talk about them as Bronsted-Lowry when we talk about proton donor or acceptors. And then Lewis acids and bases, we're going to look at, that's a W, as far as electron acceptors or electron donors. And as this type of acid or base, we're going to have to move some electrons. So I wanted to answer that question, sorry. Where do we go here? So this double bond here would move over here, and that +1 charge would end up over here, right? So this would be after that, those electrons moved. All right, so let's continue here. So what rules are there? There are rules for drawing these curved arrows to show resonance with electron delocalization. So what we want to draw here is movement of electrons that do not violate these rules. So this first rule tells us do not break a single bond. So we see here that our tail of our arrow starts at a single bond. So what would happen if we move those two electrons, we would end up with this molecule here and this ion over here. And we don't want to do that, right? We can't move electrons if we break a bond. That's not resonance. So we can never have a single sigma bond that can be delocalized. So rule number 2 is talking about the octet. So we cannot exceed the octet for second row elements. If you recall, they do not have d orbitals. They cannot have expanded octets. So these guys here, we can't have more than 4 bonds. So if we tried to move one of these lone pairs, this is a bad curved arrow because this lone pair would form a double bond here after the resonance structure was drawn, and this carbon would then have 5 bonds, 10 valence electrons that would exceed the octet. So all of these show octet being exceeded. This nitrogen has 2 bonds, a lone pair, and then it's sharing these 2 electrons here in this bond. But if we take this lone pair, right, and created that second bond, this nitrogen would also violate the octet rule. Same thing here. If we move those electrons and we drew a double bond here, that oxygen would have 10 valence electrons, so that's another bad arrow. All these are bad arrows. And this last one, again, we would violate the octet for oxygen. So this is rule 2. They all are violating Rule 2, rather, down here. So you can have less than an octet, just never more than an octet. So boron, for example, you might have looked at this as one of the exceptions to the octet rule. Say we made borane here, right? So we have borane. Oh, and we have these 3 bonds to boron. Boron only has 3 valence electrons because it's in group 3. We know that. So this is neutral. This is happy, and it doesn't violate the octet rule. And this case down here, this carbon does not have an octet. It has a +1 charge because the 3 lone pairs are on oxygen there. So in this resonance structure, this is fine. This is fine. You just can't have 5 bonds or lone pairs and 4 bonds on the carbon atom. So we'll take a look at section 2.9 in the next video.